Hi everybody, this is lecture 22, and today we're going to look at Bayesian inversion from a more practical point of view. Um, so I'm going to try to do it using an example, which is often called the rock physics problem, the rock physics inverse problem. And we're going to look at that using a Bayesian approach. So first of all, let's try to introduce the problem. Like typically in the subsurface, what we want to do is to build a model of, for example, rock and fluid properties. For example, we have a layer that we're interested in. This might be an hydrocarbon reservoir, an aquifer, whatever you want. And we want to estimate the porosity. So let's say that, for example, we don't have direct measurements, but what we can measure is the velocity of the seismic waves. So the velocity is the measured data, and the porosity is the unknown model. Well, there are in practice we actually measure seismic data, and so the problem is a little bit more complicated because from seismic data, meaning amplitudes and travel time, we have to estimate the velocity, and from the velocity we estimate the porosity. But I simplify the problem a little bit. I assume that I know the velocity of the porous rocks, and I want to estimate the porosity. So we can formulate the problem as an inverse problem because we have a bunch of models that relate porosity to velocity. For example, I give you two examples. We have Hans relationship. Now, this is an example of linear model. It's simply Vp equal alpha times porosity plus beta. Now, alpha and beta changes depending on which rock types you have, which fluid you have in the pore space. But for example, if you take alpha equal -4 and beta equal 4, you get some sort of accurate prediction so this is porosity, this is velocity. I call it VP because, well, if you're not a geophysicist, in geophysics you have generally two types of seismic waves: P waves that are called compressional waves, and shear waves, and S waves that are called shear waves. So there are models for both VP and VS. Here we're going to focus on VP. Anyway, so if you take this model for porosity equal 0, which means that you don't have any pore space, so no fluid, it's just solid rock. We are here in the plot, and the porosity and the velocity would be -4 times 0 plus 4. It's here. So the velocity is measured in kilometers per second, and the porosity is a fraction. So we start from here. 4 kilometers per second, which means 4,000 meters per second, is generally the velocity of some kind of shaly sandstone. For example, we have a percentage of clay of approximately 40%, maybe 50%. And then if we take porosity equals 0.4, 0.4 times minus, see if I can do the math quickly, 0.4 times -4 is equal -1.6 plus 4 is going to be equal to 2.4, I think, if I did the math right. So here we have a linear relationship. Well, obviously we cannot go below 0. 0.4 is approximately the maximum of porosity that you would expect in deep surface. Maybe in the shallow surface you can expect something a little bit higher than that. But that's the idea. So this is more or less the relationship that we would expect. And again, alpha and beta are actually depend on the rock type and on the fluid. Well, actually, beta is only a function of the rock type, and alpha is a function of um, the fluid, the amount of fluid in the pore space. But anyway, so this is a good example of rock physics model that is linear in porosity. Now, there are other models that are not linear, for example, Raymer's equations. It's not linear in porosity, it's quadratic. It's 1 minus porosity square times a constant, which only depends on the solid, plus porosity times, well, I'm going to call it with A and B instead of, since I use alpha and beta above. Alpha, A is actually the velocity of the solid rock, of the solid phase. So that would be the velocity if the porosity was equal to 0. And then B is the velocity of the fluid phase. So that's the velocity that we get if the porosity was equal to 1, so we only had fluid. And so this is a quadratic equation here. There's also Wiley equation. We're not going to look at that today. And I never remember how we spell Wiley. I think Wiley's equation. So the velocity is equal to 1 divided by I'm going to need other, well, I'm just going to use A and B again, although they have a different meaning. A divided by, sorry, well, let's call it U and V. U times 1 minus porosity plus V times porosity. And in this case, actually, U and V are related to A and B in the previous equation. U is actually 1 divided by A, and B is actually V is actually 1 divided by B. So essentially, U is the inverse of the velocity of the solid phase, and B is the inverse of the velocity of the fluid phase. Anyway, we're not going to look at this equation here, but I wanted to show you one linear equation. Raymer's equations is actually close to be linear for the simple reason that porosity only varies between 0 and 0.4. So even if it is a quadratic equation, it almost looks like a linear expression. And then Wiley's equation is non-linear. It's actually linear in the slowness, but anyway. So these are linear. The first one is a linear equation. The other ones are non-linear. Now, before we discuss how to use, and here, the idea is that M is going to be, the model is going to be the porosity, the data is going to be VP. Now we can have one data point or multiple data points. And then we assume now that the physics, the function f, is known. So in the past, when we did the linear fit, we tried to estimate the parameters alpha and beta. Now we assume that alpha and beta are known in the linear equation. We want to estimate the model parameter, which in this case is the model variable, which in this case is porosity, given the measurements. Um, Now, I often get the question. So I'm gonna open a parenthesis, which is gonna take maybe 10 minutes, but this might be important for your research. I always get the question, um, what if the model is not linear, but close to be linear? So, for example, you get an equation, a plot that looks like this. Well, this expression here is not too far from being linear, of course. So what you could do is simply take a straight line that approximates the model. So this is the nonlinear model, or the nonlinear equation, and then the dashed line is the linearized model. So how do we do that? So I'm going to open a parenthesis on the linearization of the model. Because in many applications, what happens is that your model is not linear, but if it is not too far from linear, what you can do is linearize the model so that you can use the theory for linear inverse problems, which is much easier than nonlinear inverse theory. So let's try to find a linear approximation of the rock physics model, or any model you're looking for. Well, what we often use is Taylor's series expansion, or series approximation. So let's forget for a second about the error. We're going to add it back later on. But we have d equal f of m. What we can do is approximate d. Well, we can put the error too. It doesn't really hurt. We can approximate d using, so we take a point m0. Which belongs to the domain of m. This is capital omega m. So any m0 that is that belongs to the model space, so porosity between 0 and 0.4. Now, typically we take the midpoint of the range, just for simplicity. And then this is going to be the value of the function in m0 plus, let's assume that we're in the univariate case. This is going to be the derivative of the function computed in m0 times m minus m0 plus epsilon. Now here, what we can do is, well, this quantity is a constant. And this quantity here multiplied by the derivative is also constant. So the variable m here is our model variable. So we just to rearrange the terms, this is equal to f m0 plus f prime m0 times m minus f prime m0 times m0 plus epsilon. Now, this is function of m. All the other terms are constant. So what we can do is say this is f prime m0 times m. I'm just rearranging the terms here. So this is f m0 minus f prime m0 times m0 plus epsilon. So now I call this quantity here g. Or, well, let's call it a. So this is a times m plus, I call this quantity here b plus epsilon. So now this is our linear expression. So this is gm plus epsilon, or epsilon, where g is actually linear. So this is an easy way to, now even if you don't remember, or if you haven't taken calculus 3 or you don't remember calculus 3, this is essentially um, what um, what a Taylor series approximation does. You take the value of a function in a certain point plus, which is this constant here, plus the value of the derivative in that point times the model variable minus that specific point. Now you can generalize it in a multidimensional domain. Um, Taylor's approximation, so this is a first order. Taylor's approximation can be done for any order. So if you want, you can add the second derivative and so on and so forth. But then it's not linear anymore in the model parameter. So this is why we have to truncate to the first order. Now, in the multivariate domain, you have d equal f of m, where d and m are vectors, and f is a vectorial function, plus epsilon. Now, what we can do is we're going to rewrite d as the value of the function in m0 plus the Jacobian in m0. So the Jacobian of f computed in m0. So this is the matrix of the partial derivatives times m minus m0 plus epsilon. Well, this is also vector. These are all vectors. Now, the Jacobian of f is simply the derivative of f1 in dm1, the derivative of fn in dm1, the derivative of f1 in dmm, and the derivative of fn in dmm. Okay. Well, sorry, I switch it. This is, I switch this to. This is, so per row we put the components of the function. And then in the columns we put the variables. Okay. So for example, if you have, I'm give you a simple example where let's say that we have VP and VS, and this can be a function of porosity and saturation of water. So the Jacobian would be the derivative of VP with respect to porosity, the derivative of Vp with respect to saturation, the derivative of Vs with respect to porosity, and the derivative of Vs with respect to saturation. Okay. Well, now we have to do the, to rearrange the terms. So this would be equal to the Jacobian of f computed in m0 times m plus the value of the function in m0 minus the Jacobian of the function computed in m0 times m0 plus epsilon. So now I can write, well, the Jacobian is a matrix, so I can write it as the matrix G. In this case, it was a scalar, now it's a matrix. So this is G times M plus a constant, which I'm going to call H plus epsilon. So it's a little bit different than the problem that we generally work on, because there is this H, but this is pretty simple. What we do is that we move the H to the left. So we subtract H from the data, which means we're basically, in the one-dimensional case, what we're doing is that we're subtracting the constant B to the measurements, which is the intercept. So we call this data tilde, and then we get our usual inverse problem. So I give an example of how it works in a multidimensional space. Actually, Hansen relationships can be extended to more than one variable. Let's see if I can do it. Well, it's a system of equation where VP is equal to, now I'm going to have several coefficients, so I'm going to add the P just to remind that this is the coefficient for the P waves, plus beta P, well, this was an alpha, times, so I'm going to have three variables here: porosity, clay content, and water saturation, and they're linked to, so the clay content means the volume of clay in the rock, and in the soil phase, and then we're going to link them to VP, VS, and the density of the rock. Plus, so beta times C plus gamma P times SW plus some intercept. Let's assume that there's no error for now. And then we do the same for VS. This is going to be alpha S porosity plus beta S clay content plus gamma S saturation plus delta S. And then the density is going to be alpha rho porosity plus beta rho clay content plus gamma rho saturation plus delta rho. Now what happens is that you can write it as a system of equations. So you get on the left Vp, Vs, and delta, and rho, which are the measurements. This is equal to, now we have to write the matrix with the coefficients. We're going to have alpha P, beta P, and gamma P, alpha S, beta S, and gamma S, and alpha rho, beta rho, and gamma rho. And then here you have the model parameters that are known: porosity, clay content, water saturation. And then you have the term with delta P, delta S, and delta rho. So this one here is not the error, it's just the intercept. So what we have to do is we move it to the left. So what the inverse problem that we have to solve is something in the form Vp minus delta P, Vs minus delta S, rho minus delta rho. Remember that these are coefficients that you know from the equations, okay? So this is our d tilde. This here was our vector d. And then this is equal to the matrix G times porosity, clay content, saturation. And now we have our usual inverse problem, d tilde equal G times M. So this is G, this is M, and I just moved the intercepts or the constant to the left and subtracted it from the data. So that's how the linearization works. In this case, well, the entire model was essentially linear, so just this was the setup. But if it's not linear, what you have to do is to take the Taylor's series approximation, truncate it to the first term, and rearrange the terms like I did here. So another example of, so this is linear multivariate. An example of nonlinear multivariate would be the extension of Raymer's equation. So we get VP, I'm just going to give you the equations here, 1 minus porosity square VP of the matrix plus porosity VP of the fluid. Vs is equal 1 minus porosity square Vs of the matrix times the square root of 1 minus porosity density of the matrix divided by density, and then density here is equal to 1 minus porosity, this one here is actually linear, times the density of the matrix times porosity times the density of the fluid. So this is an example of nonlinear model. So you have to do the linearization. This one here, I can send you the details if you're interested in, but this is not very pleasant. The derivatives are actually pretty complicated. Because these terms here, it looks like it, so, I guess I should have been a little bit more clear. So this is, it seems that these three equations are functions of porosity. Well, these three terms here are actually a function of the Clay content, and the expression is pretty complicated. And these two terms here, let's try to highlight them in a different color. So these ones here are actually functions of saturations. And these terms here are actually functions of Clay content. So you have three variables and three unknowns. And then you have the usual porosity term here, 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 and here. So this is not simple. You have to take the Jacobian, so all the partial derivatives, and this is pretty tedious. We're not going to do that, but we're going to focus on simple examples in 1D. But I just wanted to show you some applications of and show how you can set up the problem. Okay, so now that we know how to set up the problem and how to linearize it when it is not linear, what we can do is what we should do is to solve the inverse problem. Okay, we're going to do it in a Bayesian setting. So we have seen that last time. Our problem is in the form gm plus epsilon. Now, so this is a linear problem. And again, if it doesn't not linear now, you have at least one strategy that shows you how to linearize it. We assume that the errors are normally distributed with zero mean and some standard deviation, that some covariance matrix that we assume that is known. And we assume that M is distributed according to a prior model, which is Gaussian, where the mean is mu M, and the prior mean is mu M, and the prior covariance matrix is sigma M. I'm going to show you an example in a minute, but then what happens is that, so the errors are Gaussian with zero mean and independent from the datum. Independent from M. And then the model, the prior distribution is Gaussian as well. Now, it turns out that m given d, which is the solution of the Bayesian inverse problem, um, is also Gaussian. So m given d is distributed according to a Gaussian distribution with conditional mean and conditional covariance matrix. Now, the nice thing is that these two, they can be analytically computed. So there is a closed form for it. Mu m given d is equal to mu m, the prior, plus sigma m times g transpose times g times sigma m times g transpose plus sigma d minus 1 inverse times d minus g mu m. And then sigma m given d is equal to sigma m minus sigma m times g transpose times g sigma m g transpose plus sigma d, you compute the inverse, g sigma m. This is actually the covariance of the data. I guess that, let me just change a little bit the notation here. I'm going to call this one here sigma e, because this is the covariance matrix of the data error. So this is the covariance matrix of the data that we can call sigma d, and this is the cross covariance sigma md. And this is, again, the exactly the same. It's just a transpose. This is probably the most important result in Bayesian inverse theory. Because if you can make the assumption that the model is linear or can be linearized, this gives you the solution for all the possible values of the data. Now, so this is for the multivariate case. Now, if we simply assume that we're working in the univariate case, so G is 1 by 1, well, we have one parameter, one data point, and G is 1 by 1. Then we get the special case. So the matrix G is 1 by 1. So what we get now is that M is distributed according to a Gaussian distribution with prior variance sigma M. So this is the prior mean, and this is the prior variance. And then sigma is distributed according to a Gaussian distribution with zero mean and covariance and variance sigma epsilon. Then m given d is also Gaussian with conditional mean mu m given d and conditional variance sigma square of m given d. Now we just have to rewrite these two equations here for the univariate case. So this is pretty straightforward. Mu of m given d is equal to mu of m plus, now the matrix G is going to be just a coefficient. So let's call this coefficient A. So this is A times sigma m square, and then the inverse of a scalar is 1 divided by the scalar itself. So this is 1 divided by, these are all scalars, so it would be A sigma m squared times A transpose, which is still A, so this is A squared plus sigma epsilon square, and then this is D minus A applied to the prior mean. And then the variance is going to be the variance of the prior variance of M minus A sigma m squared times the same matrix times A sigma m squared. And then in this case, if you want, you can factor out sigma m squared. You get 1 minus a squared divided by a squared sigma m squared plus sigma epsilon squared. So you're going to apply these two equations in the homework. I'm going to do the multivariate case. In the homework, essentially, I'm going to give you the Hans equation, Vp equal A porosity plus B. So the only difference is that you're going to have to, so A is going to be equal to -4, B is going to be equal to 4. There's an error epsilon, which I'm going to assume is distributed according to a Gaussian distribution with zero mean and well, let's pick like a very small variance. Variance 0.01, and then I'm going to give you a prior distribution where m, well, I should write the assumptions here. And then m is distributed according to a Gaussian distribution with mean 0.2. And variance 0.09. And so I'm going to ask you to compute m given d for some value of d. And then I'm going to give you something nonlinear. Typically, so this is a typical rock physics model for velocity porosity. Then I'm going to give you a rock physics model for permeability porosity. Typically, these models, they are exponential relationships. Something like that. Now, to make it more linear, one potential approach is to work with the logarithm. And then you still have to take the Taylor's approximation, like in the midpoint, for example, and you get a linear model. So one typical equation is called Kozenik-Karman. There are several variations of Kozenik-Karman, but the most common one is that K is equal porosity cube divided by 1 minus porosity square times a constant C. So this one here looks like something like that. So typically we want to take the log of this quantity. So So K in this case is the permeability. So we work with H, which is the log permeability. Which is the log of this quantity here. This is a log 10. So then what you can do is take the derivative. So we take a midpoint porosity 0, for example, equals 0.2. And so we can write H as the value of the function. So we're going to apply essentially this relationship here. So it's the derivative let's write it this way. In porosity 0 times porosity plus that constant. This is just the value of the function in 0.2. Plus the value of the function of the derivative in 0.2. I'm going to rewrite it. So H would be the derivative times porosity plus the value of the function so this prime here is the derivative plus F, well, yeah. Okay, so now this is your coefficient A, and this is your coefficient B. So this is what you have to do in the homework. Now here what I would like to do is to try to do the multivariate case. So we're going to work on this case here with some equations that looks like Hans equations. So we have two different velocities, Vp and Vs. This one here is going to be in the form, so this is essentially this set of equations, but I'm going to simplify it by just using two variables instead of three. So we can use porosity and clay content, for example. Typically, if the clay content increases, the velocity also decreases. And if the porosity increases, if the clay content increases, the velocity decreases. If porosity increases, the velocity decreases as well. So we have, let's say, alpha P times porosity plus beta P times clay content. Let's assume that there's no constant. Well, let's put a constant here. Otherwise, this model is not physical. And then we get something similar here. So we write this model here as Vp minus gamma p, Vs minus gamma s, equal to the matrix of coefficient alpha p, beta p, alpha s, beta s, times porosity and clay content, and then we have some error epsilon. Okay, we have to pick some values. And then, let's see, this is -4. -2. Sorry, this is -6. -2. This is 5. So the first equation would be something in the form -6 porosity, -2 clay content, +5. This alpha and beta are both negative because, again, if porosity and clay content increases, the velocity decreases. And then we have something similar for Vs. This is something in the form minus, I'm looking at the numbers here, -5, -2, and 4. Okay, so this relationships here, they give you something like this. So I cannot plot 3 variables, obviously, but the VP would start from 5 kilometers per second and go down. Now, if this is for clay content equal 0, if the clay content increases, this equation would actually be shifted. So this would be for clay content equals 0.1. This would be for clay content equals 0.2, and so on and so forth. And the same for Vs. So you have a bunch of equations that are parallel to each other for different clay values. So this one here starts at 5, this one here starts at 4. This is the Vs, this is the Vp. That's the way to visualize multiple linear relations. Okay, so we have our matrix G, we have our model M, we have our data D tilde because it's a data set where we subtracted the constant. Now we have to specify a prior. So M is distributed according to a Gaussian distribution where it's a bivariate Gaussian distribution because we have 2 model parameters, porosity and clay content. We can say that we can assume that the average porosity is going to be 0.2 and maybe the average clay content 0.4. And then we have to specify a covariance matrix. Now this one here is kind of tricky to do. I'm going to just put some random numbers here, 0.09 and maybe 0.12. And then we can assume that these 2 properties are highly correlated. So let's say that we have a correlation of approximately 0.8. This one here would, so remember that the correlation is the covariance between porosity and clay content divided by the standard deviation of porosity and the standard deviation of clay content. So let's make this one here maybe a little bit bigger, 0.16. So if we do 0.8 times 0.0 0.3 times 0.4. We get something which is, okay, let's try, okay, let's say that this is 0.1, which corresponds to approximately, so this would be 0.1. I'm doing the math at the same time, so 0.3 times 0.4. This is equivalent of assuming a correlation of approximately 0.83. Okay. Well, we have to specify some variance for the data. We can just assume that sigma is a Gaussian distribution where the mean for the error for both VP and VS is 0, and then we assume that they're not correlated. We can put simply 0.1 and 0.1. Or we can even make it smaller and say 0.01. Okay, these are the assumptions. Now, what we're trying to compute is the probability of M given D. We know that this is Gaussian, so we can just apply this equation here at the top. So we're going to have that mu M given D is equal to mu M plus, I'm just going to rewrite it for simplicity. This is sigma M. So these are all the prior information times G transpose times the inverse of G times sigma M times G transpose plus sigma epsilon times D minus G mu M. We're not going to compute the covariance matrices in this case. So this is our D tilde since we modified the data. Okay, so this one here would be 0.2, 0.4, the prior mean. Then we have the covariance matrix, which is 0.09, 0.1, 0.1, 0.16 times G transpose, which is this one here. I guess I have to explicitly write G, which is minus 6, minus 2, minus 5, and minus 2. So the transpose would be minus 6, minus 5, minus 2, minus 2. Then we have to compute the inverse. So I'm going to write it here of minus 6, minus 2, minus 5, minus 2 times 0.09, 0.1, 0.1, 0.16 times the transpose. I didn't say it was easy. Plus the 0.01, 0, 0.01. And then all of this, I'm just going to write inverse here just to make it clear. And then we have times the data. So the data vector is going to be given by, well, I didn't give you the data, so I guess I have to pick a data set. I'm going to, let's see, pick a velocity of VP of 4 and VS of 3, just to make the math easy. So here we're going to have 4 minus the intercept, which is 6. Sorry, 5. And then 3 minus 4 minus the matrix G, which we have already written a couple of times now, times the prior mean, which is 0.2, 0.4. Okay. Now, I'm going to do the math in MATLAB, and I'm going to give you the result in a second. And after some calculations in MATLAB, we get 0.0754 and 0.2918. So this is the conditional mean of the porosity given Vp and Vs, and this is the conditional mean of clay content given Vp and Vs. Now, the Vp and Vs that I gave you here, so this would be, well, to be more precise, given the Vp equal 4,000 kilometers per second, or 4,000 meters per second, or 4 kilometers per second, and Vs equal 3. And then the same here, Vp equal 4, Vs equal 3. So it means that, so these are actually pretty stiff velocities. So the porosity is relatively low, pretty fast velocities. So the porosity is relatively low, 0.7, and the clay content is also relatively low, approximately 0.29. So that's how it works. Again, in the homework, it's going to be much easier because this is the multivariate case. So these are the assumptions and data. I guess I should have written the measured data here. Okay. So in the homework, it's going to be easier because you only have, will only assign you the univariate case. So essentially you have to redo the same thing, but instead of having a vector of mean, you're only going to, of means, you're going to get only one mean, and instead of the covariance matrix, you're going to get the variance. Okay, so this is a very practical approach to Bayesian inverse theory. The problem is that we have to linearize the model. So what happens if we cannot linearize the model, or the Gaussian assumption is not valid? Well, there are some methods that are called Monte Carlo methods. The idea is that we simulate from a prior distribution. So our goal is always to get P of M given D. To do that, we simulate from a prior distribution, P of M. So we get a sample that we're going to call MI. Then we compute the Fourier model, or the data prediction. So we get the data DI. Now we evaluate the likelihood that the actual data comes from the model MI. And we accept or reject the model, and we keep doing it until convergence. So that's the general idea. there are several algorithms. So the question is, how do we propose, the challenge here is, how do we propose a new model, MI, which is better than the previous one? We can, one possible approach is that we keep randomly generated models until we get one model that matches the data. But this might take forever. This is generally called acceptance rejection sampling. So we keep randomly guessing until we find the solution. Well, this is not necessarily the best approach. We would like to learn from the previous simulated models. So there are some subfamily of methods, which is called Markov chain Monte Carlo. Where the new solution is somehow related to the previous one. So I'm going to write here the steps. So we have several algorithms. There's Metropolis, Hastings, and Gibbs sampler, and other choices. But the philosophy is essentially the same. So we first sample from the prior distribution. And we get a sample that we're going to call M0. So we're going to build the solutions in an iterative way. Now, so we're going to iterate over the number of solutions, the vector of solutions. So given a solution xi, we want to generate a solution, mi, a solution mi plus 1 in 2 steps. So in step 1, we draw a candidate . I'm going to call it M prime, from a proposal distribution. I'm going to call it this distribution Q, which is a condition distribution M prime given Mi. Well, let's call this one here M nu. Now, in step 2, I'm going to accept the new solution with some probability. Now, in Metropolis Hastings, so this is the most common algorithm, in Metropolis Hastings, this probability is given by the probability of accept is given by the minimum of a ratio of probabilities, which is the probability of the prior probability of M nu times Q, the probability of X, oh my goodness, M I given M nu, divided by the probability of Mi times the proposal distribution of M nu given Mi. and we take the minimum between that and 1. So if accepted, then mi plus 1 is equal m nu. If rejected, we keep the same model as before. So mi plus 1 is equal to mi. Now, this is typical of Metropolis Hastings. Oh, well, and then the last step is that we iterate until convergence. Well, there are some differences in the other algorithms. If you just use Metropolis, what happens is that Q is symmetric. This means that Q of mi given m nu is equal to Q of m nu given mi. So at this point, the probability of accept is simply the minimum between the ratio P of m nu divided by P of mi and 1. Which means that if P of m nu is greater than P of xi, we accept m nu. Instead, if P of m nu is less than P of mi, I keep writing x, then we can still accept m nu, but with probability P of m nu divided by P of mi. So look at this expression here. If P of m nu is greater than P of mi, this ratio is greater than 1. So for sure we're going to accept it because the probability is going to be 1. So you always accept m nu. If P of m nu is less than P of mi, then this quantity is less than 1. So the minimum between something less than 1 and this ratio here, 1 is the ratio. So we can still accept m nu, but the probability is not necessary, is not 1, so there's a chance that we're going to reject it. There are several choices of the proposal distribution. Typically, we choose a Gaussian distribution because it's easier. But the idea is generally that we have to choose the distribution such that we can randomly cover the model space so that we don't fall into local minimum. Ideally, you also want to keep the probability of acceptance large enough, because otherwise it means that you don't have enough variability in the solution. If you look at the convergence plots, typically you get something that looks like this. So this is the number of iterations. Well, the misfit between the data and the prediction generally rapidly decreases, and then eventually it stabilizes. Well, it's generally something like this. So you have a rapid convergence, and then you have some variability here, which is the stochastic nature. So you can use the models after you reach convergence to compute some statistics like the mean and the variance and so on and so forth. Now, this is, I don't expect you to be able to use these methods, but this is just a very rough, a very brief introduction to MCMCs. So if you hear Monte Carlo Markov chain Monte Carlo methods, you know at least what we're talking about. This is essentially a method where we propose a new solution every single time by sampling from a distribution because we don't have the analytical solution like in the previous case. This is still a Bayesian method, but it's not for Gaussian distributions and it's not for linear problems. It's more general than that. Okay, I think I'm gonna stop here. Instead of discussing data fitting, which is something that probably you have already done in MATLAB or you can do in MATLAB very easily, I would like to discuss basic concepts of geostatistics, because if you work in geosciences or even in engineering, you might need some tools to interpolate and simulate variables in the spatial domain. So this is going to be the topic for the next couple of lectures.